Okay, so this session is about MOSFET. So this is AEC module 2.1 and 2.2 revision. Today's date is 8/9/23. Can you see what I am writing over here live? Just reply in the chat box, in the chat. Yes? Okay, fine. So we will be covering briefly 2.1, and 2.1 is all about MOSFET working. MOSFET working, its IV characteristics, okay, and its construction and types. So we'll be briefly devoting around let's say around 45 minutes for 2.1, and for 2.2 we have MOSFET biasing. So basically in MOSFET biasing we will be covering various biasing circuits, okay, and here we will also cover around we plan to cover in 45 minutes. So we'll this is a plan. So let us start with MOSFET. Okay, MOSFET. All right, it's actually called as metal oxide semiconductor field effect transistor. Okay, that is its full form, metal oxide semiconductor field effect transistor. All right, and its types are as follows. So the types are it can be classified into depletion type MOSFET, so depletion MOSFET, and enhancement MOSFET, enhancement type MOSFET. In the short form we write D type and E type. Okay, under depletion type we can have NMOS, N channel MOSFET D type, and P channel MOSFET D type, depletion type. In enhancement also we can have NMOS E type, this is enhancement, and PMOS E type. Alright, so in short we have to explain the construction, working of these four types of MOSFETs. Alright, understanding? And we will start with NMOS enhancement type MOSFET. Okay, at the end of in few minutes, okay, you will get to understand what is the difference between depletion type MOSFET and enhancement type MOSFET. Alright, so let's begin with NMOS. So the story over here doesn't begin with MOSFET first. First it begins with this device. Let's say that you have this metal layer, this is my metal, and then you have an insulator in between, and this is, let's say, here we have P silicon substrate, let's say P silicon is there, and here we have metal. Okay, so this is my metal and this is my base, so that is called as B substrate. Okay, this is called as body or substrate. Okay, and this is called as gate, G. Alright, now let's understand the working of this two terminal device, and then we'll extend the working to MOSFET. Alright, so now this is insulator in between, this is oxide layer, this is oxide, SiO2 oxide. So we will study three cases over here. The three cases are, we'll study the application of voltage Vg negative, then we'll study application of voltage Vg positive, small value, and then we'll study the application of Vg positive voltage large value. What happens in this? Alright, can you hear me? Everything alright now? Can someone reply?
Yeah, sir.
Okay, so please concentrate. Metal is made up of lots of electrons, And what is p silicon made up of? Lots of holes, right? It's a p silicon material. So this will have lot of holes and this will have lot of electrons. Now we apply negative potential. So that means gate is connected to negative voltage as comparison to body. Okay, so this is negative, this is positive. So now tell me what will happen if I have this kind of a situation. So here Vg is negative. What will happen to these electrons and what will happen to these holes? Tell me. This is an insulator, so no carrier can flow through the insulator. Okay, so tell me what will happen. Hello. So these electrons which are present over here, these electrons cannot be attracted towards the negative side of the battery, so they will remain as it is over there only, and they will be pulled towards the oxide layer, but oxide cannot have any conduction of electricity, so these electrons will remain here only. What about these holes, these positive potential of the battery? These holes will be, what will happen, there are many holes over here, right? They will be starting to accumulate near this interface. So there will be holes accumulating near the surface. Okay, so if I apply a negative value of Vg, if I apply Vg more and more negative, then more and more of these holes will get accumulated over here. Are you understanding? Because there are holes inside p-type silicon. Okay, and because of this positive potential they will repel back, so there will be an accumulation of region. So this region is called as, this is accumulation of charge carriers. Okay, so this region of operation is called as accumulation. So this is not useful. If we apply a negative voltage to a MOSFET, to a N MOSFET, it's not useful at all. It's basically a two element device, a two terminal device right now. Got it? No carriers can flow inside. Okay, let me check who wants to join the meeting. Please join the meeting via your Somaya email ID. So please inform Tejas to join via Somaya email ID. Okay. Okay, fine. Let me continue. So you have understood accumulation region? Clear it is? Yes, no? Hello?
Yes, sir.
Okay. Next, we take this device again. This is metal, this is oxide, and this is p-type semiconductor again. Now we apply positive potential. Okay, Vg is positive but small value. So now what will happen, you tell me? So here Vg is positive but small value. What will happen? These holes, I mean for the electrons, they will be attracted towards the positive end of the battery, but that's it. No carrier can flow through the oxide layer. Okay, so no current can flow through the this material actually. Okay, so tell me what happens to the holes over here. Some of these holes will get attracted towards the negative end of the battery, right? So whenever a hole leaves a position, what they leave behind? Whenever a hole leaves a position, what it leaves behind? Immobile carrier, no? Yes or no? So it will leave behind immobile carriers. Okay, like this. Actually plus 1. Now these immobile carrier will form a depletion layer. So this region is devoid of any charges. Okay, and why it is happening? Because holes from here over near the surface are being attracted towards the negative end of the battery. Okay, so region near the surface, this surface is called as SiO2 interface. Okay, so near the SiO2 interface, beneath that there will be a depletion layer or depletion region, and this mode of operation is called as depletion mode of operation. Okay, this is not yet MOSFET है, ये MOSFET नहीं बना है. It's a two terminal device having a gate and a substrate body, that's it. Okay, so understood what happens over here? Holes leave their position, and whenever they leave their position, they leave behind immobile carriers, charge carriers. Did you understand this? If yes, I can move ahead. Yes or no? Hello?
Yeah, sir.
Okay. Now, for the third case, this is important. So, we have metal, we have oxide, and we have p-type silicon. And now we are connecting over here gate and body. This is gate, and now we are applying a positive potential but a higher value. So we are applying Vg, large value. Okay, let's say large value is how much? Let's say 50 volt or 100 volt. All right. So now what will happen? There will be depletion region, of course. That depletion region will be there. Okay, consisting of these carriers, right? Let me just yeah, these carriers will be there. Okay, there will be a depletion region. So this is my depletion region. I'm not drawing the immobile carriers for simplicity. So this is my depletion region. What will happen now if I keep on increasing the carriers? If I keep on increasing the voltage, here the voltage was around very less. It was around, let's say 0 to, let's say, around 5 volt or so. So that's a quite small voltage, even smaller than that, 0 to 2 volt or something. Here we are applying 0 to 100 or 50 volt. So what will happen now? See, remember, in p-type silicon there are electrons also, few electrons, minority carrier electrons are also there, na? Yes or no? So over here there will be few electrons, very few of them. But as we go on increasing the voltage, there will be increase in the thermal temperature also. Okay, more and more voltage you apply, more electric field will be created. Okay, more powerful electric field will be there, and due to that these electrons, they will be repelled by this negative end of the battery. This is negative, no? So like charges repel, right? So what will happen is these electrons will, as you slowly increase the voltage, will start accumulating near the surface, SA. Okay, and then you increase the voltage more, so more thermally generated carriers will generate, and more of these carriers will fill over here. So when you increase the voltage further, let's say 40, so more carriers will be there. If you increase it to 50, more carriers will be there. Okay, so in this way, within this area you have lots of negative carriers. So this layer is called as N layer, so we call N inversion layer. So what has happened is, inside the p silicon we have created a N layer full of lot of electrons, lot of free electrons. And why that is happening? That is happening at a higher voltage, because we are increasing the voltage, so thermally we are increasing the temperature also. So more and more minority carrier gets increased, and these minority carriers are getting repelled by this battery, and they are depositing underneath the silicon silicon interface, silicon silicon dioxide interface. Got it? And this is the inversion layer. This is called as inversion region, inversion mode of operation. Did you understand this? Did you all understand this? Why the N layer is created, and how it is created at a very heavy voltage, high voltage? Yes or no? Hello?
Yeah,
Sir, inversion layer won't have any positive charge in it.
Inversion layer will have positive mobile carriers, but there are so many. I will, if I draw that expand version, let me draw that. It has immobile carriers. Let me draw it once again, like this, right? So this is full of charge carrier. There are so many of them generated. Okay, so what will happen is immobile carriers are there, but right now they are not increasing anymore. After a particular point, they are not increasing anymore, because holes are not leaving the position. In fact, electrons are getting attracted towards it. So depletion region is there. These immobile carriers are there, but I am not showing it for simplicity. That's what I am saying. Are you understanding?
Yes, sir.
But the minority carrier concentration is increasing so high that only focus is that these electrons gets deposited near this region. That force is more, rather than the holes getting attracted over here, the electrons are getting pulled up towards the SiO2 interface. So this is what the concept is. Now listen carefully. Now we are coming to MOSFET. So the limitation of this is that we require very high voltage to achieve this. Now what if we want to achieve this at low voltages, what we will do? So what we will do is, we'll build a MOS device, we'll build a MOSFET, metal, oxide and semiconductor, that's fine. But this is gate and this is body, that's fine. But we do one more thing, we take this out further and we make two more deposits over here of N plus, N plus, N plus, okay, like this. And we call the base as open ground, like this. So common base, like this. So this and this won't be there now. Let me complete this. Okay. So we have this layer now. Did you understand? So this is my P silicon. This entire thing is my P silicon. Did you understand how did I manipulate it? This is P silicon. This is my source terminal. This is my drain terminal. Got it? Understanding? This becomes my MOSFET. So this is my metal layer. You can draw the structure also. This is my metal layer. This is oxide and this is semiconductor. So metal, oxide, semiconductor, field effect transistor. Got it? Now how does it help? How does it help? Please understand. So let's see this creation of inversion layer. First let me draw the depletion layer. Okay. So how does the depletion layer look like? See, remember this is like a PN junction, right? So whenever there is a PN junction, there will be a formation of a depletion layer. Let me draw that very light depletion layer. ये मेरा depletion layer है. Okay. This is my depletion layer. Okay, this is my depletion layer. Okay, present. Now, what is the advantage of adding N plus and N plus source and drain? Okay, so it's like now we have achieved this gate voltage, you have achieved it inversion layer at a very large voltage. Now if you want to achieve at a lower voltage, what you do is you add two N plus deposit materials, two diffusion layers, N plus and N plus over here. Now whenever the electrons gets accumulated near the SiO2 interface, and now you apply drain to source voltage, you apply the voltage over here, so electrons from here, this N side will contribute to the conduction now. It's like a dam, right? Let's consider that you have two reservoirs of water. Okay, two reservoirs of water, one here and one here. Okay, and in order to connect them, there you have to dig a hole in the ground. Okay, so you dig a hole in the ground like this. Start digging the hole in the ground like this, like this, like this. And when the hole in the ground completes this and complete this, the water from here and the water from here can join together, right? Yes or no? Yes, this is dam number A, dam B. So whenever the two dams are open, it can be connected. This length can be connected if the hole is digged. So same thing is happening over here. Okay. So whenever these carriers are getting accumulated, getting formed near this thing, SiO2 interface, beneath the SiO2 interface, now you apply drain to source voltage. So this electrons from here will also contribute to this, and the electrons will flow like this. See, the electrons will flow like this and reach over here. They come out of the terminal. So this is my N region. This is called my N region. Okay, and this is the channel. This we call it N channel. Are you getting it? Hello? Did you follow now what happened? And this, since we are connecting source and drain, this we can achieve it at a much lower voltage, at a gate voltage of around, let's say, 3 volt, 4 volt also we can achieve this channel to be formed. Okay, and the distance between this source and drain is called as channel length. This distance over here from here to here, this is called as channel length. L is called as channel length. So you remember you're hearing about that 45 nanometer technology is there. Okay, so 45 nanometer means the active channel length. This is the technology node, right? So 45 nanometer means the difference between the distance between the source and the drain is 45 nanometers. All right, and this oxide layer is made up of SiO2, and metal is aluminum or polysilicon. So metal is made up of aluminum. Alright, so this is my metal oxide semiconductor field effect transistor. Alright, now this channel is formed with the application of voltage VGS and VDS. Okay, so before applying any voltage there was no channel, right? So channel is getting formed over here, right? So this type of MOSFET is called as enhancement type MOSFET. Enhancement type. And why it is NMOS? Because the substrate you take is P silicon, okay, and the source and the drain region are N plus. So this region is called as N channel MOSFET. This is N channel MOSFET, short form we write it as NMOS. Okay, this we can also write it as N channel MOSFET, which is same as NMOS. Are you following what I am saying over here? Please, reply. Hello. Yes or no? Few more students, please reply. You all are following what I am explaining? The MOSFET, why there is MOSFET, and why there is N plus and N plus source and drain regions are there, diffusion regions.
Yes, sir.
Do you have any doubts right now?
So can you repeat why it's called enhancement type?
Yeah, I will repeat why it is called enhancement once I discuss its characteristics. See, what happens is, before applying any voltage, there is no voltage applied. Is there a channel formed over here? No, na? There is no channel, na? This N channel is not there, right? Yes or no?
Yes, sir.
Ha. So with the application of voltage, this N channel is getting formed. Okay, so that's why it's called as enhancement. Actually, it has another explanation also that I'll explain when I discuss the characteristics. Is this fine? Is this fine now, up till now?
Yes, sir.
Okay, now this is the construction of the MOSFET. Now we'll go for the working. Okay, so this is, you can draw this out. So we will discuss again MOSFET working. How does it work? Okay, it will include construction also. So all of you please draw the diagram. Please draw this diagram, what I am drawing over here. So you have this is P silicon substrate, and inside that P silicon substrate you take two N plus diffusion layers like this. Okay, and above that you draw oxide layer. Oxide layer I have shown in this. Okay, and then above that you draw a metal layer. So this is my metal layer. Okay, and in the new technologies they call this as P plus, they call it as a body terminal, but body terminal we rarely use, but still I am showing it. This is the body or the substrate terminal. This is source terminal. This is gate terminal, and this is drain terminal. So these are the contacts. These things which I have drawn are the contacts. Okay, and this is P silicon substrate. So this is your construction of a N channel MOSFET. This is NMOS. For NMOS you take P type silicon substrate. This is the substrate or the body. Okay, we have a metal, we have a gate. This is made up of aluminum. This is the metal made up of aluminum, and this is my oxide layer, which is made up of SiO2, I request everyone to kindly mute, please. Okay, this is the construction. Alright, body terminal normally is connected to the ground, so even if you don't show it, it's fine, but it's there. You remember it's there. It's a 4-terminal symbol: body, substrate, gate, and drain. And I'm going to explain the working of it. All of you have drawn the diagram? All of you ready? Hello?
Yeah, sir.
Okay. Now remember, there are two electric fields over here working. Two electric fields are there. So since you have already written over here, let me reduce this things. There are two electric fields. There is something called as a vertical electric field, like this. Vertical electric field, I'll call it as EY, and there is horizontal electric field. Let me call it EX. Now tell me, which electric field will be active when? So whenever we apply any voltage between gate terminal, okay, gate and source, whenever we apply a voltage between gate and source, see, body and source are connected to ground always, okay. When I connect a voltage at the gate terminal positive, right, I need to apply positive, so this is my VGS. Whenever I apply this voltage VGS, which electric field will be responsible? EY. And this electric field will be responsible for pulling the minority carrier electrons near the surface. So as I increase the value of VGS, these electrons will go on depositing over here. Okay, means they will start accumulating near the surface. All right, did you understand? So this EY is responsible for VGS voltage. Okay, it will be directed like this. It will be responsible for, see, electrons will move in the opposite direction to the electric field. So as I can say, if the electric field is directed this way, the electrons will try to move up opposite direction, right? So it will come up above and they will make a N channel. This is the condition. Okay. Now EX will be responsible whenever we apply a voltage VDS. So I'll take this part. I rub the above diagram. Okay. Now whenever we apply the voltage VDS, drain voltage positive, the electric field which will be active will be EX. So EX is responsible for VDS. What this will do? This EX electric field, it will be directed like this, right? Like this. So this electric field, what it will do is, for electrons in the source region, let's say the channel is formed, okay, the electrons from the source will move over here inside the channel and they travel towards the drain terminal. So the source terminal is the source of carriers, right, and at the drain terminal the electrons are drained out. Okay, now we know that the conventional direction of current is opposite to the flow of electrons. So electrons are going over from the drain to source, so current will go from source to drain. So this current is ID. So current flows like this in the circuit, the yellow color portion which I have marked this way. Can the current flow like this over here? Can it flow through the oxide layer? Never. So it will flow around the loop in the N channel, and that's how you will get your operation of MOSFET proper. Is this okay? Now we'll start with the working slowly. This much you have understood? Which field is responsible for what? Can we start with the working, everyone? Any doubt anywhere before I proceed? There is vertical electric field and horizontal electric field. So EY will be responsible for the electrons in the p-type silicon substrate, so deposit near the SiSiO2 interface. And EX electric field will be responsible for the electrons from the source region to travel to the drain region. Is this clear to you, everyone? This much is okay?
Yes, sir.
Okay, now listen carefully. Now we'll slowly go in the working of it. Okay. Now, there is a particular voltage. There is a particular voltage at which this device turns on. So this voltage is called as VGS should be greater than threshold voltage, VTH. Okay. So write down, this is threshold voltage. You know, for the silicon diode, what's the voltage to turn on voltage? 0.7, right? Similarly for the MOSFET, this is the threshold voltage for N channel MOSFET. It is also called as VTO or VTN. Okay, VTH, threshold voltage. So what this threshold voltage is? So whenever VGS is greater than this threshold voltage, N channel will be formed, guaranteed. Okay, so N channel will be formed whenever VGS is greater than VTH. So yeah, that is the condition. Got it? So N channel will be formed like this. Let's say inside I'm not showing the carriers. These dots are my electrons. Let's say. So this is my N channel. So this will be formed only when VGS is greater than VTH. So write it down. For VGS less than VTH, your current ID will be 0, right? Your device will be off, right? So this condition is called as cutoff region of MOSFET. Your current is 0, VGS is very small, VGS is positive but very small, and it is less than VTH. So no channel will be formed, no channel formed. Okay, so this is the first step of working. Everyone understood this? No channel is formed, no current flows. Okay, now for the second case, VGS is greater than VTH. Okay, so channel is formed, N channel is formed. Build a current flow in the device. If we apply only VGS voltage, so VGS is positive voltage greater than VTH. Build a current flow. Hello. Build this ID current flow if we just apply VGS voltage and not apply VDS voltage. So here we say VDS is 0, it's not applied, and we have just applied this voltage VTH. So can you tell me what will happen now? Nothing. The current is eligible to flow. Now MOSFET is eligible to conduct, but it does not conduct because there is no phase difference between drain and source potential, right? Drain and source potential, there is no difference at all. Okay, so we cannot have any current flow. So here also current is 0. Okay, now when we apply VGS greater than VTH and we apply VDS also, when we apply VDS also, then the channel is formed. Now the current flows. So this region is divided into two parts. One is called as linear or ohmic, and other is called as saturation. Now we'll understand what happens to the MOSFET when it is in the linear region and what happens to the MOSFET when it is in the saturation region. Okay, so here what happens, we have applied VGS and we have also applied VDS. So when we apply VGS and VDS together, then the current flows in the device. Is this point up till now, whatever we have discussed, it's clear? Any doubt you have? Tell me.
Excuse me, sir.
Hello?
Hello.
Okay, great. Now we'll slowly build it up now. Okay. Now we'll go to the characteristics. We'll explain via characteristics now one by one. Okay. So this is VDS voltage. This is ID current. This is output characteristics. Now, let's say that we have applied VGS. Let's bring the scenario over here. We have applied VGS voltage such that is greater than VTH. Let's say this is 1 volt. So we have applied VGS as 1.5 volt. Let's say that. Okay. So VGS is greater than VTH, N channel is formed. N channel formed. Okay. So this is 1.5 volt. I mean gate voltage is 1.5, this drain voltage is 0. Okay, and now we apply VDS very small value, positive small. Okay, let's say that voltage is 0.2 volt, 0 to 0.2 we have increased. So drain voltage is at 0.2, source voltage is 0 volt with respect to ground. Source is grounded. Alright, now you remember there is a depletion layer. I hope you have not forgotten. There is a depletion layer here, like this. This is my depletion layer. So now this channel is formed, and now we have applied 0.2 voltage. So that means drain to, are you listening? Hello, everyone?
Yes, sir.
Now we have applied 0.2 voltage, so drain voltage is at 0.2 volt, source voltage is 0, gate voltage is at 1.5 volt, source voltage is 0. So now tell me, what is VGS voltage? 1.5 now. VGS voltage is VGS voltage is 1.5 volt. And what is VDS voltage? No, not VDS. VGD. VDG voltage, how much it is? VD is 0.2 and VGD, sorry. VGD voltage. VG voltage is 1.5 and drain voltage is 0.2. So how much it is? 1.3 volt, correct? Yes or no? Tell me.
Yes, sir.
Yes,
Okay.
sir.
So that means gate control over the source is 1.5 volt and gate control over the drain region is 1.3 volt. तो थोड़ा सा loose हो रहा है control, right? So that means we are applying over here drain to source. This is 0.2 volt, right? Okay, and this voltage is 1.5 volt and this is 0 volt. Okay, so remember we are applying a positive 0.2 volt to N region. So this is a PN junction, it will become reverse bias, it will become slightly more reverse bias. This is 0, right? So normal PN junction, when they are formed, there is a depletion layer, so this is slightly more reverse bias. Okay, but still the current, since this is positive voltage applied and here it is negative voltage applied over here, 0, right? So even if it is 0 volt, there is a negative voltage applied, so the electrons which are over here will start to travel onto the other side like this. The electrons will start to travel from here and they will try to reach the drain region, but the current will be very small. Okay, so the current will increase linearly first. At first it will increase linearly, so very small value, 0.2 volt. VDS is 0.2 volt. Okay, so ID increases linearly with VDS because is the conductivity part is straight, right? Nothing is happening, that's it. The electrons are going from the source region to the drain region via this N channel. Clear it is? For the small values of VDS, is this thing clear to you? Please respond. Yes
Yes,
or no?
sir.
Now we go to the next case. Now instead of 0.2, we applied a higher voltage. VGS is same, huh? Now we applied a voltage 1 volt, let's say. So drain to source voltage is 1 volt. So this is at 1 volt, this is at 0. Now tell me how much is VGS and VGD? Hello?
VGD is 0.5.
Yes, this is 0.5 and this is 1.5, right? मतलब gate का control over source, gate to source voltage, gate control over the source is 1.5 volt and gate control over the drain is 0.5 volt, correct? VGD is 0.5 but this is 1 volt, no? This is 0 volt. So what will happen now is this shape of the N channel will reduce, will try to influence. Earlier it was straight line, right? Now it will become like this. Please concentrate over here. Now because of the more reverse voltage over here, the channel conductivity will be less at the drain end because gate ka control over the drain is less because it is 0.5 volt, right? And gate ka control over the source is 1.5 only. So this channel will get tapered. Are you understanding? This channel will get tapered because gate to drain control is less and gate to source control is same as it is. Are you getting it? So this is 1 volt now. You know how the 1 volt is getting distributed, right? 1, 0.9, 0.8, like this over the channel. So drain to gate voltage is more. Now what happens to depletion layer? Yes ma'am, 1 second. Yes ma'am.
सर मुझे ऑनर्स का ये देखिए ना अभी था 22-23 का रोल कॉल लिस्ट अगर आपके पास है तो
मैं भेज
हाँ मैंने मेल किया था उसको ही रिप्लाई करो
भेज yeah. So your drain voltage is 1 volt and source voltage is at 0 volt. Okay, how will be depletion layer? Depletion layer at the source side will be same as before. but depletion layer at the drain side will be tapered more. Why it is more? Because you are applying 1 volt to N plus. So this depletion layer will be more. Now this is a PN junction, right? This is PNN, and this PN junction will not change because it is 0 volt. Okay. So this gate to substrate become more reverse bias. This PN junction becomes more reverse bias than this. So that's why, because of this tapering, your N channel gets reduced. So now what happens? The conductivity of the channel reduces. So the electrons flow. Okay, electrons start flowing. That is not changing, but the conductivity of the channel is reducing. So because of that, what happens? The current falls. The current slope falls. So current curve slope will be falling down. Are you understanding? It will not be at the same rate. It will fall. This will fall due to the conductivity of the channel is reducing. You are getting it? Yes or no? Hello?
Yes, sir.
Okay. Now we apply drain voltage as drain to source voltage as 1.5 volt. So this is 1.5, this is 0 volt. How much is VGS? 1.5. How much is VGD? VG is 1.5 and VD is 1.5. How much?
0.
Yeah, 0. That means gate ka control over the drain is completely gone, right? See, gate is acting like a control terminal. So gate ka control over the drain is gone. Gate ka control over the source is 1.5 volt. Okay. So what we do is, here N channel will be completely disappearing from the drain end, because gate ka control hi chala gaya, right? So like this. Okay. This is the condition. So electrons will be there, but the channel will disappear at the drain end. It will go completely, because ये देखो ना, VGD 0 volt, it has no control. So channel at the drain end will be gone. Will the current flow? I mean, will it reach the maximum value? Yes. So what will happen is, current will reach the maximum value now, and will continue to remain at a point, at a maximum point. So this is the 1.5. How much it was? 1.5 volt VDS, right? Okay. This is ID. So current has reached over here. Now after that, what will happen? Now we are increasing the VDS voltage, right? Did you understand this much? 1.5 है तो gate का control over the drain will be gone. Gone means gone. So channel N channel will disappear at the drain end. It will be only there over here. And what about the depletion layer? Depletion layer will extend even more. Depletion layer will be like this. Even more. This will be increasing more. Depletion layer width will increase now as we increase the reverse bias voltage. So that is what is happening. Is this understood? So this region of operation is called as edge of saturation. इसको बोलते हैं, your MOSFET enters edge of saturation. Are you getting it? Yes or no? Can I proceed further? Hello?
Yes.
Okay. Now I'll do opposite. So now here I'll apply 1.8 volt. So here it is 1.8. What is VGD? Tell me fast. Minus 0.3, na? Yes or no? Hello, tell me, calculate. VG is 1.5
Yes.
and drain voltage is 1.8. So what will happen? How it will affect the channel is
0.3
minus 0.3.
minus 0.3.
VG minus VD, right? So what will happen due to this? There will be a reverse voltage here also, right? So channel conductivity will be completely gone over here. देखो इधर देखो difference देखो. Earlier it was ending at the drain terminal. Now it is ending a little earlier. So this condition is called as channel pinch off. Channel is getting pinched off over here. Pinch off. Okay. So here it is pinch off at the little left value. The little left it has gone. Are you understanding?
Yeah.
So channel is getting disappeared at the drain end, and it's moving towards the source end. Why it is so? Because right now the gate to drain voltage is minus 0.3 volt. Okay, and now if I mean what will happen now, what should happen, will the current flow, will the current flow? So the current will be here, electron will be flowing over here, but here there is a gap, here there is a gap. What will happen? This depletion region will be even more. Let me draw the depletion layer. Will be even more, very very powerful. So these electrons will be there, but there is nothing to travel. I mean, it doesn't even touches the drain region. So will the current become zero, or will something else will happen? Tell me.
It will saturate.
Yeah, it will be constant. So what happens is, I'll tell you example. Ideally, what should happen is it should fall to zero, but it doesn't fall to zero. It actually saturates. It remains constant like this. And this is at one value of VGS. VGS1 is equal to 1.5 volt, let's say. Okay, greater than 1.5. This is a constant VGS value. Okay, so this is how the characteristics will be. Okay, now why it remains constant, that is the thing I am telling you. Earlier, let me draw over here and show it to you. So let's consider this as, let's consider this as SiO2 interface. Okay, and this is my drain region, and this is my source region. So the channel is getting disappeared over here, right? Correct. So what happens in this region? And of course this is my oxide, and over here I have my gate. So this is gate, this is oxide layer. Oh, oxide, and this is my gate terminal. Okay, this I am showing this only. So electrons over here, they enter into this N channel. This is my N channel. Huh? And not drawing anything else for simplicity, they come over here and they have a very short distance to travel. Now remember, your drain region is tremendously reverse bias. This is very heavy voltage. Let's say this is my source terminal, this is my drain terminal. You remember you have a depletion layer. The depletion layer over here is very very large, like this. So whenever depletion layer is very large, you say the electric field is very very powerful, very very powerful, right? Earlier the channel length was what? The channel length was entire distance between source and drain, right? ये था ना channel length earlier, ऐसे था ना? This was L, right? Now the effective channel length will be this much. ये इतना हो गया. Earlier electrons have to travel from source to drain. Now they have to travel from this area to this area, and there is a tremendous electric field, very high electric field. So what happens is, as soon as the electrons come over here, the electric field is directed very powerfully in the opposite direction, like this. It's a very powerful electric field. So under the influence of the electric field, the electrons are accelerated are driven towards the drain region, and they come out, of the drain region like this. So these electrons are being pulled towards the drain region by the very powerful electric field, but they will be moving at a constant velocity. Okay, so listen, whenever you drop a stone from a height, initially it accelerates, but when it hits before it hitting the ground, it will attain a constant velocity. Same concept is over here. Okay, so this concept is that the electrons travel via drift mechanism. So if we plot electric field versus drift velocity, this is electric field, Vd is drift velocity, the velocity with which the carriers travel, electric field. This graph saturates at a particular value. This E will saturate at a particular value of drift velocity. So here, okay, are you understanding? See, the electrons are traveling with a velocity. That velocity is called as drift velocity. Okay, so after a particular time, this drift velocity will remain constant after they reach the critical electric field. Okay, and that is happening over here. The length is becoming very small. Now how you define electric field, anyone knows? So if I have a semiconductor, N-type semiconductor, and I have defined over here voltage, this is N silicon. Okay, how will the current flow? Electrons will be going from this side to this side, right? So electric field will be directed this side. This is electric field. How it is defined as voltage upon length or volt per centimeter. So if I reduce my L, if I reduce the value of L, what will happen to electric field? Tell me. If I reduce the value of L, what happens to electric field? It will increase, no? E
Yes.
increases if L reduces. Yes or no? Hello?
Yes, sir.
So right now, the channel length is what? This is, okay, wait it until it gets clear. Yeah. So right now, what is the electric field Ex? And what is the voltage applied Vds? And what's the length delta L? Now this delta L is very, very small. Huh? This delta L is very, very small. Okay. If L is 45 nanometer, if L is 45 nanometer, you can imagine delta L will be very small. It will be less than, let's say, 0.5 nanometer. Now nanometer is what? 0.5 into 10 raised to minus 9 meters. Okay. So here VDS is also very, very high and delta L is reducing. So what happens to electric field Ex? It becomes very powerful. Do you agree? Yes or no? Hello? So under the influence of this electric field, these electrons which are at the end of this N channel travel swiftly towards the drain region and they come out, and then it constitutes drain current. Okay, that's how the current becomes constant over here. Instead of accelerating, it will be constant. Alright, did you understand the working? This is how the N channel MOSFET works. Hello? Any doubt? Yeah, students? Now, whatever I have told, just increase this 1.5 to 2.5 volt. So what will happen? What will happen? The graph will look like this. The graph will look like this. This is for higher value of VGS. The graph will increase, yeah, like this. So this is 1.5 volt, this is 2.5 volt. It's increasing, and if you increase more voltage, see, as you can see, the current level is enhanced. So ID level is enhanced. With VGS, right? So if ID is enhanced, this is also called as enhancement type MOSFET. So as you can see, current characteristics is enhancing by increasing the value of VGS. So we can say your VGS controls ID. And what is my saturation point? See, this is at 2.5, right? So this might be 2.5 volt. It will reach at 2.5. Okay, VGS is 2.5, right? So its saturation point might be here. So this curve, how will you differentiate which is my region? This is my linear region. This is VGS minus VT curve. Huh? This is VGS minus VT curve. So first case mein VGS is 1.5 and VT is 1 volt, let's say. So 0.5 rahega ye. Very, very small it will be. So this is called as linear region. Okay. And this region where the current saturates is called as saturation region. This is saturation region. And where is my cutoff? Cutoff will be somewhere around here. It will be on the x-axis itself, where VGS is less than VT, like this here. I'll not draw, simplicity. So cutoff will be on the x-axis. This is VGS less than VTH. So this is my cutoff region. Did you get it? Hello? On the right hand side of this curve, this side, this is the VGS minus VTS locus. So on the right hand side of it, we have saturation region, left hand side we have linear region, and over here whenever VGS is less than VTH, it is cutoff region. So did you all understand the characteristics and the working? Please say yes or no. Little
So
bit.
the saturation part, the for two graphs, the end of saturation part, the points which we have plotted, from there we've got the third graph. The highlighted one graph, and that part is linear region, right?
Wait. I will be explaining transfer characteristics again, so don't worry, I'll explain this again. But did you understand the overall working of the MOSFET?
Yes, sir.
Okay, got it. Now I will be drawing, focusing only on the characteristics part. Okay, now listen carefully how to draw it. I am only showing the drawing part. I hope you have understood this. Now draw the characteristics in your books. This is VDS. Okay. Let me just save the document first. Yeah, this is VDS. This is ID, and first I will draw the first graph. Let me draw that curve first. Okay, now I will draw the characteristics. So this is one number 1, then we have number 2, then we have number 3. Okay, so this is VGS3, this is VGS1, this is VGS2. All are greater than one another. Okay, this is 1, VGS 2, and this is 1. Let's say this is 1.5 volt, 2 volt, 2.5 volt. Alright, understanding? And all are greater than, here VTH is, let's say, 1 volt. So all are greater than VTH value. Okay, now this region over here, this curve is called as VGS minus VT locus. Okay, now tell me these points, what are the values? This is VGS is 1.5 and VTH is 1, so this will be 0.5, right? Are you getting it? So the first curve, the saturation value, at what value of VDS it reaches? 0.5. So this will be how much? 2 minus 1, so this will be at 1 volt, right? Yes or no? And this will be 2.5 minus 1, let's consider this 2 volt only, 2.5, 3 volt. So this will be 3 minus 1, this will be 2 volt. Are you getting it?
Yes, sir.
So to the right hand side of this graph is my saturation region. To the left hand side of this is my linear region. So this area is my linear region. This yellow color, entire. This is linear region, or it is also called as non-saturation region or ohmic region also. Okay, and the cutoff will be on the x-axis. Did you get it? Now this is output characteristics. Okay, output characteristics of which device? N channel enhancement. Now did you understand the enhancement, why it is enhancement? Because current is getting enhanced by increasing the level of VGS. Yes or no? Now similar to this we have transfer characteristics. Okay, we don't have input characteristics in a MOSFET because current cannot flow inside the oxide layer, right? So Ig is 0 in case of MOSFET. Let me draw the transfer curve. This we assume it at VDS equal to, let's say, 10 volt hai. Okay, and we draw ID versus VGS characteristics. So we take the point from here only. Okay, we take the point from here only. We take the points from here only. We take the points from here. So what is VGS over here? 1.5, right? Somewhere around 1.5 volt. Here it is 2 volt and here it is 3 volt, and we join the points together. You extrapolate these points, and that's how you get the graph. ऐसे. So this is my graph. Actually I have over exaggerated it. ऐसे graph रहेगा अपना. Not exact, but this is how the graph will be, and these points will be coming from here on this graph. Did you understand this graph? Hello?
Yes,
This,
sir.
this is called as transfer characteristics. Okay, of NMOS enhancement type device. Alright, and over here the MOSFET will work in the saturation region in this transfer curve, because VDS is 10 volt and VGS is greater than VTH. So this voltage over here, this voltage will be greater than VTH value. Then the current starts flowing. So this is my transfer and working of N channel enhancement type MOSFET and transfer and output characteristics. समझ में आ रहा है ये? Did you understand? Yes, no, what? Okay.
Yes, sir.
And this curve is given by this equation. Write down the equation. ID will be equal to Kn times VGS minus VTN the whole square. ID equal to, write it down over here. Let me reconnect my tab. Okay. This equation is given by, this is only defined in the saturation region. Kn times VGS minus VTN the whole square, where Kn अगर चाहिए तो Kn is W by L mu n COX, this is half W by 2L mu n COX, this is the value. Mu n is the mobility, COX is the gate oxide thickness, W is the channel width, L is the channel length. Alright, and then in the exam this equation will be more useful. Understood? Now what are the symbol? Now there are two symbols for this. One is 3-terminal symbol which looks like this. Okay, this is 3-terminal symbol, gate, drain, source. There is another one also, 4-terminal. Here the arrow is inward. The 4th terminal is the substrate terminal. This is drain, gate, this is body terminal, and this is source terminal. So this is 4-terminal symbol. This symbol for NMOS enhancement type MOSFET. Have you drawn? Can I move ahead? Hello? Ready? Hello? Okay. So what are the voltage conditions for the MOSFET to be in the cutoff region? So MOSFET is in cutoff region, we know ID is 0. What are the conditions? VGS should be less than VTN. Okay. Second is, what is the condition to be in linear region? For it to be linear region, ID flows. But what are the two conditions? VGS should be greater than VTN and VDS should be less than or equal to, write down these conditions, VGS minus VTN. Okay. So VGS minus VTN is what? This one. If VTN is 1 volt, VGS is 1.5, this will be 1.5 minus 1.5. So VDS has to be less than or equal to 0.5. Matlab I am saying the left hand side of this curve is my linear region. And if this is above, MOSFET will be in saturation region. In that case, ID saturates, so ID flows. And under two conditions are VGS has to be greater than VTN and VDS has to be greater than VGS minus VTN. So these are the conditions. Did you get it? Everyone? Is this clear to you? Please write it down. Hello? Completed?
Yes, sir.
Okay. Now let's go to, this was about N channel enhancement type MOSFET. Okay. Now I will draw the characteristics for other types also. So let's consider PMOS E type. What will be the symbol? the symbol will be, arrow will be inwards. This will be drain, source, sorry, this is gate, and this will be source terminal. Okay, and 4 terminal symbol also you can draw it similarly. So for a p channel MOSFET, what it is made up of, the base material will be made up of N silicon, and this will be p plus, this will be p plus. No need to draw this if you don't wish to. This will be your gate terminals, this will be your gate terminal, this will be your drain, this will be your source. All the voltage polarity reverses and the current will reverse in case of p channel MOSFET. So here what channel will be formed? P channel, made up of holes. Okay, and what are the characteristics? Draw the characteristics. So as I have told you, the current voltage directions will be different. So instead of writing VDS, I'll write VSD, and this will be, current will be positive actually, sorry. So here you will get different graphs for different voltages. So this here you will have VGS negative instead of positive, and your threshold voltage will be negative. So here we can write minus 1.5 volt, minus 2 volt, minus 3 volt. Okay, this is the output characteristics of NMOS, PMOS, E-type MOSFET. What will be the transfer characteristics? Anyone? ID will be positive, right? So this is VGS. How will it look like? It will look like this. It will go like this, reverse. Okay, and this is your threshold voltage, VTH or VTN, VTP actually. Alright, this will be the graph, and this ID will be given by ID Kp times VSG minus mod of VTP the whole square. This is the equation of current. This is not so much utilized, but still I just told you to, for your information. Have you drawn the graphs? Can we move on to the next type? Hello?
Yes.
Okay. Now very important, we will be starting with depletion type MOSFET. So now you will understand what do you mean by depletion type MOSFET. See, enhancement type MOSFETs are, see, when I showed over here, if nothing is present, if we apply nothing over here at the input side, at the gate terminal, if no voltage is applied, no channel is formed. So basically enhancement type MOSFETs are called as normally off devices. So enhancement type, E-type are normally off device, whereas depletion type MOSFET are normally on device. Alright, and its construction is the same, almost same. So let's say we are discussing NMOS D type. So we have N plus source and drain, then we have the gate oxide layer, then we have the gate. This is oxide, this is the metal, and this is gate terminal, this is oxide, this is the drain terminal, this is the source terminal. You know what is the difference? The difference is that here the channel is already present. Okay, so here N channel, this is the N channel, right? Let me use a different color. So here the difference is that N channel is already present, is already formed, without even applying any voltage, is present from the start. And now what do? We apply the voltages, mera device, if we apply gate voltage as 0, it's on. And now we applied more and more VGS and VDS voltages. You apply VGS voltage, you apply VDS voltage. So the device will go from on state to off state now. Okay, so that's why it's called as a depletion type MOSFET, because we are depleting the N channel over here, and your device is going from on state to off state as we go on increasing the value of VGS and VDS. Did you get it? So in enhancement mode, N channel was not present. It is getting formed with the application of voltages, and in case of depletion type MOSFET, N channel is already present, and if we apply more and more voltages, the channel will get disappear. Did you understand the difference? Enhancement and depletion?
In enhancement type, the device goes from off to on and
Yes,
vice versa in depletion.
correct. It's normally on device, and here it is, your enhancement mode is normally off device. So we go from off to on, and depletion type we go from on to off. Got it? Rest, working wise everything is same. ठीक है? Can we move on to the characteristics now? Hello?
Yes, sir.
Okay. So the characteristics, good news is that it's almost similar. Okay. Only thing is that you draw the characteristics, please, everyone. I'll tell you the reason why they are different slightly. So this is one, this is second. Okay. That's it. And it can also have one more. It can have VGS 0 also. VGS can be -1. Here you require negative voltage to turn off, right? Negative voltage to turn off. -1, and it can be positive also. So VGS can be 0 also, negative also, positive also. So that's the major difference in depletion type MOSFET. Whereas in case of enhancement type, you can only have positive values of VGS, right? Yes or no? So here VGS can take 0 value, positive value, or negative value. All three are allowed. So this is the, the line of bifurcation. So below this we have depletion mode. Above this line we have enhancement mode. So VGS is positive, it is working in the enhancement type MOSFET. This depletion type MOSFET also can work as enhancement mode when VGS is positive. But when VGS is negative, it's working in depletion mode. And this is my output characteristics. Now I'll draw the transfer characteristics. It's derived from here only. So output transfer characteristics will be like this. ID versus VGS. So this point where the current becomes 0 is called as the pinch off point. This is VGS. And this point when the current reaches the maximum is called as IDSS. And this curve is represented by ID is equal to IDSS 1 minus VGS upon VP the whole square. Okay. So in this expression, if I substitute VGS equal to 0, what will I get? ID, IDSS, right? And if I make ID equal to 0, what will be my VGS? Will be equal to minus VP. So that's why you got these 2 points. Got it? Hello? So this is for depletion type MOSFET. VGS goes to positive values also and goes to negative values also. This comes from here only actually. It's an extrapolation of these curves only. Are you following? From here only we get. Hello? Did you all understand? Hello? So over here, this is my D mode and this is my E mode. What will be the symbol like? Symbol will be, symbol will be slightly If you want to draw 3 terminal symbol, you have to show a dark line over here indicating that the channel is present. So this is my drain, gate, source. In terms of 4 terminal symbol, you draw straight line instead of dash line. So this is gate, drain, source and body. So these are the symbol for NMOS depletion type. Got it? Hello? And for the, let me show you the last one. So for P channel depletion mode MOSFET, this will be the graph. Can you see this graph? This is ID versus VSD, same P channel depletion mode MOSFET. So the graph will be like this. VGS, if you have to apply positive values for it to be in the depletion mode, for enhancement mode is -1, negative values, and this will be the graph. VGS and VP, VGS and ID, and VDS and ID. So this is for P channel MOSFET. So will you make this graph on your own, everyone? Hello?
Yes, sir.
Okay. Now we'll solve one numerical and then we will, go for the 2.1. 2.1 will be over. So let's say that in an enhancement type device, gate voltage, this is connected at 5 volt, this is connected at 3 volt, this is connected at 0 volt. So find region of operation of MOSFET. So how will you find out? And VT is given as 1 volt. So which type of MOSFET it is first of all? It is NMOS enhancement type MOSFET. And VT and voltage is this. So what is this voltage? This is phi. This is drain terminal, gate terminal, source terminal. So how much is VDS? VD minus VS, it is 5 volt. How much is VGS? VG minus VS, which is 3 minus 0, this is 3 volt. So how to check the condition? See, first condition is VGS has to be greater than VTN. So is this satisfied? Yes. Second condition is we have to check if VDS is greater than VGS minus VTN. Let's check it out. VDS is how much? 5. And this is 3 minus 1. Yes, this is also true. So if these conditions are true, the given device is in saturation mode. Did you get it? How to identify the region of operation for the MOSFET? Yes or no? Hello? Did you understand this? Okay. So with this we complete module number 2.1. Revision of it. 2.1, 1.2 I'm writing. 2.1 is completed. That is MOSFET working, construction, characteristics and region of operation. Okay? Anyone having any doubt? Any doubts in this?
No, sir.
Okay, now for 2.2, I'll tell you. So 2.2 involves MOSFET biasing. This can I cover at a later time because there are two types. We have depletion type biasing, depletion type MOSFET, biasing. Then we have enhancement. Let me write it, then you will understand what I am saying. Enhancement type MOSFET biasing. Under depletion type we have three types. First is zero bias circuit, second is self bias, and the third is voltage divider bias. Okay, here we have also two types actually in enhancement type MOSFET biasing. First will be drain feedback bias, and second is voltage divider bias. Got it? So we have to analyze them and solve numericals on it. So this will take around another 1.5 hours. So is it okay if I continue later today again at a different time, because now there is a break time and I have a load at 2 to 4. So can I continue today after 4:15 again till 4:15 till 5:15, whatever time we'll get? Is it fine?
Yes, sir.
Yes, sir.
Okay, so this I will complete it today around 4:15. So I will not send an email. So 4:15 p.m. again meet me, or we'll start at little early, 4:10. So same link, join together, and then I will explain about module number, these all things. This is your module number 2.2, zero bias circuit, self bias, voltage divider bias. I'll discuss all three. I'll solve one numerical on it, and enhancement type biasing, I'll solve both of them, the drain feedback and voltage divider bias. Okay, fine. So that's all for today. I'll resume on 4:15 today again, 4:10 again. Okay. Any questions, anyone?
No, sir.
Okay. Yeah. So that's it from my side. So next revision session will be today 4:10 p.m. There I'll discuss module number 2.2.
Sir, for small signal hybrid